Okay, so what we've been doing so far has been, we're talking about the integral, right? We said that it's a hard thing to evaluate integrals, but fortunately we have this wonderful theorem, the fundamental theorem of calculus, that says that if you can find an antiderivative of your function, then you're good, right? The definite integral is just going to be the difference of the antiderivatives of the antiderivative at the endpoints, right? And that was the fundamental theorem of calculus 2. The fundamental theorem of calculus 2 comes out of fundamental theorem of calculus 1, right? Which was that you can always make an antiderivative as that area function guy, right? Okay. And then from there, right, we said, okay, now that we have the second fundamental theorem of calculus, we're going to do all these other things that sort of allow us to extend our ability to use it, right? So we have U substitution, right? It's the first trick to extend your application of the theorem, and then we had integration by parts. We have these trigonometric substitutions, and we have partial fraction decomposition, right? Okay, those are the main ways of extending the reach of the fundamental theorem of calculus, so that you can evaluate definite integrals. But all of them rely on the fundamental theorem of calculus. So that is, they rely on you having an antiderivative. And so what we're going to talk about just for a little bit is what happens if you don't have an antiderivative. What happens if you don't have an antiderivative, right? If somebody says, say, what's the definite integral of e to the minus x squared from 1 to 2? Okay, like how would you approach this problem at this point? You'd hope maybe that you could find an antiderivative, but in fact, there is no simple way to write down an antiderivative for this function. Okay, so it's not so easy to do using the methods we've introduced so far. Okay, so instead, today we're going to talk about numerical approximation. So what's called numerical integration. So getting approximations of definite integrals. Getting approximations of definite integrals. Okay, so just going backwards, let's recall, right? When you talked about the integral in the first place, one idea is to say, well, let's take a to b, and we divide it into n parts, right? So divide into n parts, right, of equal length. Right, so b minus a over n is going to be the length of, you divide this full interval into n subintervals, and each one is going to be b minus a over n. Okay, and then one way of approximating the integral is to do something called the right endpoint approximation. Right endpoint approximation. Okay, so what you do is for each of these points, let's call them x0, x1, x2, x3, all the way up to xn. Okay, so on each of these intervals, you're going to take the right endpoint, and you're going to evaluate the function there, you evaluate the function there, and then you make a rectangle of that height. Right? You make a rectangle of that height, and you multiply by the width of the base, and you get this, the area of this rectangle. Okay, so you say f of x1 times b minus a over n, right? And then you do that for each interval. So you're going to do x2, right? F of x2 times b minus a over n plus blah, 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 f of xn times b minus a over n, right? And so this would be the nth right endpoint approximation of the definite integral. Okay. Right, and you see how the picture is going to look. You take the right endpoint, make a rectangle, take the right endpoint, make a rectangle, take the right endpoint, evaluate it, make a rectangle, etc., etc. Right, here you gotta get this one. Okay. So, maybe that's one thing you could do. This is, if somebody wanted you to get the integral of e to the minus x squared dx between 1 and 2, maybe that's something you could do. Right? You could say, okay, I'm going to divide 1, 2 into n parts, and then I'm going to approximate by using a right endpoint approximation. Okay? And that would give you some number. Okay, so this is maybe the simplest way of getting some number. There are sort of slightly more sophisticated ways. So more sophisticated, right, is called the trapezoidal approximation. Okay, so you can probably guess what happens here. Probably can guess what happens, right? You have your function. You have your function a, b, like this. And then you divide, you divide the base into n parts. So n pieces, x0, x1, xn, right? Okay. And then what you do is you say, okay, I'm not going to use this. I'm not going to use these rectangles. Instead, I'm going to use trapezoids. So I'm going to evaluate the function at each of those points. Okay, you evaluate the function at each of those points, and what you do is instead of taking one of them, right? Instead of taking so with the right endpoint approximation, we would use this guy as our height, but instead of doing that, we're going to make a trapezoid like this. Okay. So you connect the two endpoints, you get this approximation, right? And you sort of suspect that that's going to be better. That's going to be a better approximation than the left endpoint approximation or the right endpoint approximation. So it's a simple idea, right? Everybody okay with that? Right. Nothing fancy. Okay. So if we think about it, let's call these heights y0, y1, y2, y3, etc., etc. So let's let the heights be denoted. Let y sub I be f of x sub I. Okay? So the height at x sub I. Okay. what is the trapezoidal approximation? What's the trapezoidal approximation? Well, what's the area of this trapezoid? What's the area of this first trapezoid? Okay, so y something plus the sum of the y's, right?
Multiply by
b minus a over n,
and then over 2.
and then divided by 2, right?
Yeah.
Right. Everybody see that? Right? Because you have, this box is right. The area of the lower box is just y naught times b minus a over n. The area of the lower box, right? The area of this lower box is y naught times b minus a over n, right? The area of the upper box is going to be y1 of b minus a over n, right? And then this is the average. This is the average of those two, right? The area of the trapezoid is going to be the average of those two boxes, of those two rectangles, right? Right. Okay. So what you get when you add it all together, right? The nth approximation, which we're going to call T sub n, the nth trapezoidal approximation is going to be b minus a over 2n, b minus a over 2n times y naught plus 2y1 plus 2y2 plus 2y minus 1 plus y sub n. Right? Because it's b minus a over n times y naught plus y1 over 2 plus y1 plus y2 over 2 plus yn minus 1 plus yn over 2. Right. So you see how you evaluate. Okay. Right. So is that clear? Is that derivation clear? Okay. So if I said give the value of the, say, I don't know, the fourth trapezoidal approximation of the integral from 0 to 1 of x squared dx, right? Then what would you do? Okay, take 1 minute and just write down what you would need to do to calculate this. Yes. 4. Here we're going to use n. This is the 4.
Only 4.
Yes, just for, I mean, for right now, yeah, use 4. We'll take n to be 4. Right, so I'm asking what's t4? What's t sub 4 for this integral? Okay, turn to somebody nearby and talk with somebody nearby, please. Hansi, why don't you talk with Wang Pi? Wang Po, why don't you talk with Chen? Chen and Hao, I don't know. If you want, you can talk to the people in front of you. Okay, so what do we need to do? Would somebody like to say what needs to be done? Okay, what do we need to do? Anybody? Does anybody know? Right, so here we have the integral 0, 1, right? We have a function x squared. Right? We want to get an approximation, so what do we do? We want to get the fourth approximation, so divide into 4 parts. Okay. Do you want to talk? No, you don't. Okay. All right. Divide into 4 parts, right? So we have a fourth, 2 fourths, 2 fourths, 3 fourths, 4 fourths, right? Okay. And then, right? So, and then what do you do? 1 4. Right. So you need to evaluate the function at those points, right? So you've got y0, right? y0 is 0, y1 is 1/16, y2 is, 1/4, and then you've got 9/16, and then you have 1, right? So you have these different heights, right? You've got 0, you have 1/16, you have 1/4, you have 9/16, and then you have 1, right? Those are your y's, right? 0, y0, y1, y2, y3, and y4, right? And then you just evaluate, right? So you say, okay, I'm going to get b minus a over 2n, right? b minus a over 2 times 4, and you have y0 plus 2y1 plus 2y2 plus 2y3 plus y4. Right? So 10, 10, 14, 10 eighths, 14, 14 eighths, 22 eighths, 11 eighths. Right? So 11 over 64. Right. So you take your function, you divide the interval up into n pieces. You evaluate it, right? And so you divide it into n pieces, and then you just take the areas of these trapezoids, right? You take these areas and you add them together, right? You add them together, right? The area of this first guy is going to be
Number is wrong.
is it wrong? Did I mess up? Maybe.
It should be n over
11 over 32? Let me see. So here I have 1/8, I've got 1/8, I've got 4/8, I've got 5/8, I've got 13/8, and then I have 5/8, 14/8, 22/8, right? Oh, I'm sorry. Yeah. 11 over 32. Sorry. Thank you. Yeah. Okay. Right. Which is pretty good, right? Because we know that the real answer is 11 over 33, right? It's 1/3. Right? The real answer should be x cubed over 3 between 0 and 1. In other words, 1/3. So we're off by a little bit. Wongdi, you look a little, are you lost? You came in late, so if you're lost, go ahead and ask.
Because my numbers and the different numbers.
Yeah, what did you do?
I don't know, I thought y0 is 0 plus y1 is 1 over 16 and then over 2 and plus.
Yeah, so these are the same things. These are the same things. This expression up here and this expression down here are the same thing. So if you want, you could do it this way, but it's probably easier to do it this way. Okay, so you could, right, you could say it's going to be 0 plus 1/16 over 2 plus, 1/16 plus 1/4 over 2 plus 1/4 plus 9/16 over 2 plus 9/16 plus 1 over 2. Everything times 1 over 4. Right? You could do that, but it's the same thing as doing this. It's the same thing as doing this, right? Because you can pull the 2 out, right? B minus A over 2, and you get y0 plus y1 plus y1 plus y2 plus y2, right? So you get y0 plus 2y1 plus 2y2 plus 2y sub n minus 1 plus yn. Right? So it's the same thing. Okay. So either way. Okay. Either way, you get the same thing. Okay. Everyone all right with getting the approximation? It's very you just follow the rules and you get it. There's not much thinking involved. Although it's good to understand what you're doing. Okay. Here is the more interesting part. How bad? How wrong are we? Right? Can we determine a bound on our error? Can we determine a bound on the error? Okay. And the answer is yes. There's this nice theorem which gives you a control of the error. It says if f double prime is continuous on AB, then the error which is the difference between the actual value and the nth approximation, right, of T sub n, is actually controlled by b minus a over 12n squared times m, where m is a bound on the size of the second derivative on AB. Okay, maybe I'll say, let me write it this way. If f double prime is continuous on AB, and the absolute value of f double prime is controlled by some m on AB, then the error is controlled. The error is going to be smaller than b minus a, sorry, mistake, b minus a cubed times m over 12n squared.
What is
The error, like how wrong you are. Like, this is your approximation. This is the actual value. So the difference between the actual value and the approximation, like how wrong you are. So for example, if we look at the approximation we just did, right? So our function was x squared, right? The second derivative is 2, right? So you know, it's continuous and it's bounded by you know, the number 2. So we know that the error is, we know that the error is going to be 1 cubed over 12n squared times 2. Okay, actually for us we were taking n equals 4. So in the previous example, right, our n was 4, right? That's 16 here. Okay. So that gives us a control on how wrong we could be. Right, 1 over 96. So we know that our approximation, if we didn't know what our real answer was, right? If we didn't know what our real answer was, at least we know that our answer was within 1/96th of the answer we got of our approximation. Okay, because you know, it's you know, it's kind of silly to do a problem whose answer you know already. Okay, so suppose we didn't know the answer. Well, we know that, you know, this was within 1/96th of the true answer. Okay, is this making sense to people? Anyone have questions? Anyone have questions? Okay, so this is kind of interesting, right? Because you see how the error shrinks with n, right? You see how the error shrinks with n, right? 1 over n squared. So as your n increases, right, your error shrinks like 1 over n squared. Yes, well.
does f equal the second derivative of f?
It is a control on the size of the second derivative. It's not the second derivative, but it is just any number that's bigger than the absolute value of the second derivative, right? So bigger than the second, any number bigger than the second derivative. Let me do another example. That will help clear it up, make it more clear. Okay. So here's an example. Somebody asks you to get a trapezoidal approximation of this function. Right. So let's think about what's the error? What can we say? What can we say about the error of t sub n? What can we say about the error of t sub n? Okay, well, we know that the error, the nth error, let's call this thing e sub n. We know that the error is going to be bounded by b minus a, that's pi, cubed over 12n squared times some bound on the function, right? Some bound on the second derivative. Okay, well, we need to do the second derivative, right? So if we take the first derivative, if we take the first derivative, right, you get the first times the derivative of the second plus the derivative of the first times the second, right? If you differentiate that again, you're going to get the first times the derivative of the second plus the first times the derivative of the first times the second, right? And so you end up with negative x sine x plus 2 cosine x. Right? That's the second derivative. Okay. And what we're hoping is to get some control on the size of this thing. So let's look at the absolute value of this. What bound can we, what upper bound can we get on this when x is between 0 and pi? Okay, I'll do it for you, right? Say, well, what do I know about this? I know that this is smaller than negative x sine x plus 2 absolute value of cosine. Right? Right. Just by the, the absolute value of a sum is smaller than the sum of the absolute values, the triangle inequality. Right? It's a triangle inequality. Okay. Further, I can get rid of the negative sign, right? And I can write this as the absolute value of x times the absolute value of sine, right? Plus 2 the absolute value of cosine. Right? Well, what do we know about the cosine? How big could the absolute value of the cosine be? How big is it? Well, we're between, as x ranges from 0 to pi, what can we say about the cosine?
Maximum is 1.
The maximum is 1, right? So this thing is smaller than 1. And what about the sine? The sine also, its maximum value is smaller than 1. And what about x? As we range from 0 to pi, x could be unless pi, right? So what do we get? That the second derivative is controlled by pi plus 2. Okay. The absolute value in the second derivative is smaller than pi, definitely smaller than pi plus 2. Okay. So we can use that as our m. Okay. So we'll use that as our m. Pi plus 2. Okay, and that will give us good bound on the right. So we get pi cubed pi plus 2 over 12 times 1 over n squared. Right. So that's how wrong our nth approximation. That's the worst our nth approximation could be.